This video contains the solutions to take-home problems number 25. There's a couple different techniques that we use when we're solving equations involving logarithms, but the first one is to realize that whenever we have two logs of the same base, in this case we've got log base 7 on the left and log base 7 on the right, with different things plugged into those two logarithms, then the two things that we plugged in have to be the same. And the reason is that because the function y equals the log base 7 of x is a one-to-one function. And that means that if the two y values that we get, think of this as a y value and this is a y value, if the two y values they would have to be equal, then the two x values that we plugged in have to also be equal. That's the way that we think about a one-to-one function. So that means that x plus 3 has to equal 4x minus 12. Now, when we want to use this technique, it's very important that we don't have anything else in the equation. We don't have anything being added or subtracted outside the logarithms or multiplied or anything like that. It's just a log equals a log, then the things inside have to be equal, assuming the bases are the same. It's very similar to the technique that we use to solve exponential equations when the bases were the same. So now that we have this equation, we do the typical things that we do: subtract x from both sides, add 12 to both sides, divide both sides by 3, and we get x equals 5. It's important, though, to make sure that when we plug this back into our original equation, that we're not doing anything illegal, like taking the log of 0 or of a negative number. So the log base 7 of 5 plus 3, we just want to check and make sure that that really does equal the log base 7 of 4 times 5 minus 12, but that just gives us the log base 7 of 8 equals the log base 7 of 8, and that checks out. This is a similar problem. We've got log base 2 of one expression equals the log base 2 of another expression. So again, because the log is a one-to-one function, these two expressions have to be equal. Now this equation is a quadratic equation, so we have to remember how to solve those. We get x squared plus 6x minus 16. We can factor x squared plus 6x minus 16 into x plus 8 and x minus 2. So we get x equals negative 8 and x equals 2. Now again, we need to go back and check to see if these really do work. So let's check x equals negative 8, and what we see is the log base 2 of negative 8 squared minus 16. We want to know, does that equal the log base 2 of negative 6 times negative 8? And on both sides what we get is 48 inside our log, and the log base 2 of 48 really does equal the log base 2 of 48. But when we try x equals positive 2, something different happens. We get the log base 2 of 2 squared minus 16. And we want to know, does that equal the log base 2 of negative 6 times 2? Well, the problem here is that we get the log base 2 of negative 12 and the log base 2 of negative 12. And even though those are the same, those are both undefined. We can't take the log of a negative number, and that means that we can't plug 2 into this equation without breaking our mathematical rules. So that means that we have to throw away the solution x equals 2, and the only solution that actually works is x equals negative 8. Now here's an example of a function where, or of an equation where we only have one logarithm. And so now the technique that we're going to use is to rewrite the equation in exponential form using the definition of the logarithm. Now remember that the definition of the logarithm is that y equals a to the x if and only if the log base a of y equals x. In this case, my a is 4, the y is 5x plus 1, and the x is 2. So that means that when I rewrite this equation in exponential form, I get 4 to the 2 equals 5x plus 1. 4 squared is 16, and so we can solve our equation. Subtract 1 from both sides, divide both sides by 5, we get x equals 3. And again, we should go back and check and make sure that when we plug 3 back into the original log, that we're not taking the log of 0 or the log of a negative number, but it checks out, and so this is our solution. Now here again we have an equation with only one log in it, but notice that there's a lot of extra stuff on the same side of the equation as the log. So the first thing that we're going to need to do is get that log by itself on one side of our equation, and then we'll be able to rewrite the equation in exponential form. So the first thing we'll do is subtract 5 from both sides. And then we'll divide both sides by 2. And then we will rewrite the equation in exponential form. So we get 2x minus 1 equals 3 to the 3. 3 to the 3 is 27. Add 1 to both sides, divide both sides by 2, we get x equals 14. And again, we should go back to the original equation, check and make sure that when we plug in 14, we're not taking the log of 0 or the log of a negative number, but again, this time it works out. Last example, again, similarly, we've got a log with some extra stuff on that same side of the equation. We've got to get the log all by itself before we can rewrite this in exponential form. So what we need to do is multiply both sides by 10. That's going to give us the log base 10 of x plus 10. Again, there's no canceling or, crossing out tens or anything like that that's going to work here. So we really just have to get the log by itself and then rewrite in exponential form. 1/5 times 10 is 2, and now when we rewrite this in exponential form, we get x plus 10 equals 10 to the 2. 10 squared is 100, so this gives us x plus 10 equals 100. Subtract 10 from both sides, and we get x equals 90.